Our next form of proof that we're going to look at is a proof by contrapositive. Now remember, if P then Q, the contrapositive of that is not Q, then not P. So we're going to use that idea. Okay? Recall that an implication is logically equivalent to its contrapositive. So that will be the structure of our proofs. There are plenty of examples of statements which are hard to prove directly, but whose contrapositive can easily be proved directly. This is what we call a proof by contrapositive, and that is what it does. Okay? It proves something by proving the contrapositive. Okay, it gives, let's look at that statement at the top of the next page. It gives a direct proof of the contrapositive of the implication. Okay? This is enough because the contrapositive is logically equivalent to the original implication. Okay, so what does it mean? The skeleton of the proof, if P then Q, by contrapositive will always look roughly like this. You assume the negation of Q, you explain, and therefore the negation of P is where you're heading for. Okay, so as before, there are variables and they're quantifiers. The quantifiers are always either universal, which means they are true for all values, or they are existential, so they exist for certain values. We set them to be arbitrary elements of our domain. Okay, so let's look at a few examples that deals with the proof by contrapositive. Okay, let's look at our next statement. It says, is the statement for all integers n, if n squared is even, then n is even, is that statement true or not? Okay, we can attempt a direct proof. A direct proof of this statement would require fixing an arbitrary value for n and assuming that n squared is even. So let's say we fixed n, we assume n squared even. Now what does that mean? That would mean that n squared can take on the form of any even number, which is twice an integer. Okay, it's a multiple of 2. But now what does that tell us about n? Well, I don't think it hardly tells us anything about n, because if I want to now say something about n, I need to work on that side with the root of it. Now that's not guaranteed to be an integer, which is a multiple of 2. So in this case, a direct proof will not help, because it just does not want to do what we need it to do. So no, direct proof is out. Let's look at something else. Let's write down the contrapositive of this statement. Okay? Once we've written down the contrapositive, we get that for all integers n, okay, for all integers n, let's write it down. For all integers n, where n is an integer, for all values of n where n is an integer, okay, if the contrapositive now, if n is odd, then n squared is odd. This looks a little bit more promising though. Our proof will look something as follows. We define n. We suppose that n is not even. What this then means, we assume n is not even. So in other words, we're assuming it's odd. What does it mean when it's odd? And blah, 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 blah. Therefore, what does it mean for n squared being odd? And that's the structure of our proof. Okay, so let's start with that proof. We will prove the contrapositive. Okay, now the contrapositive, remember, said not the one, and therefore if not the one, then not the other. So let n be an arbitrary, that's just another way to say it's any integer, so it's an arbitrary integer, n. We suppose, or we assume, n is not even. Okay, so what does that mean? It means n is odd. Okay, and we'll come back to that now. What does it tell us about that? Well, it tells us that n is 2k plus 1 for some integer k that we can use. In fact, for any integer k, that will be the form of the odd number. Okay? Now we've done that. We've said what it is, what it looks like, and now we're going to see how it works for n squared. So what happens to n squared? Well, n squared is the square of this defined form of n. Now if we distribute that, we get 4k squared plus 4k plus 1. Now we do what we did earlier. We group conveniently the first two together. We remove a 2 only because we want to show that this is the form of the n squared. Then the n squared will indeed be odd. Okay, so what is this? This is 2k squared plus 2k that remains behind once we've removed the common 2 there. Okay, now what does this mean? Well, since 2k squared plus 2k is an integer, what does it tell us? Well, n squared takes on the form of an odd number. Okay, now once we've done that, we can therefore conclude, therefore n squared is indeed odd. Okay, so we've proved it, and we've proved it by contrapositive. Now if the contrapositive is true, then the initial statement will be true as well. So this is an example of a proof by contrapositive. Okay, here's our next example. It asks us to prove that for all integers a and b, if a plus b is an odd number, then a is odd or b is odd. Notice the or, not the and. Now the problem with trying to do this as a direct proof is that it will be hard for us to separate a and b from knowing something about a plus b. We need to know something about this to be able to separate them. And on the other hand, if we know something about a and b separately, then combining them might just give us information about the sum of the two. Okay, so we go to the contrapositive. The contrapositive statement for this proof will be the following. For all integers a and b, for all integers a and b, if a and b are even, then a plus b is even. Okay, that's the contrapositive statement. said, used to say for all integers a and b, if the sum of the integers is odd, then a is odd or b is odd. Now we're turning it into its contrapositive. For all integers a and b still, if a and b are even, so it discounts the possibility of them being odd, then the sum is even, which takes away the possibility of being odd. Okay, I hope we understand that. So the structure of the proof will be as follows. We're going to introduce what a and b is, that they're integers. We're going to assume that they are both even, and then we're going to move towards proving something about their sum. Okay, so let's start with our proof over here. We're going to introduce our variables. So let a and b be integers. Okay, then we're going to assume both a and b are even numbers. Now we've dealt with this quite regularly so far. So we're going to say there exists, what do we call it, a k and an l, such that k and l are both integers. Okay, and what can we write them as? We can write a as twice k. That directly shows its evenness. And b as twice l in this case. Okay, so there we have two statements. We've got a and b that are integers. We're assuming that they're both even numbers. What is the implication for this? It means that a is even, b is even. And now we're on our way to say something about their sum. So therefore, what will a plus b be? Well, a plus b will be 2k plus 2l. By just a simple substitution of these two, I can remove the 2k plus l and argue that which is an even form. Why is it an even form? Since k plus l is an integer, and twice an integer creates an even number. Okay, we've added two integers together, so the result is an integer, and twice that integer creates an even number. Okay, and that completes our proof. So therefore we can say that a plus b is indeed even in this case, and there's our proof concluded. Now note that our assumption that a and b is even is really the negation of a and b being odd. Therefore we used which laws? We used De Morgan's laws for this proof. Okay, I hope that made sense to you. Okay, our next example that deals with proof by the contrapositive is as follows. Consider the statement. For every prime number p, either p is true or p is odd. And they ask us to prove this. Okay, now how can we rephrase this? If I rephrase this, we can say the following. That for every prime number p, if p is not equal to 2, then p is odd. Okay, it's the only even prime number that we have is the number 2. This is what's basically asking us to prove, that all other prime numbers are indeed odd. Okay, so let's do our proof. For our proof, we're going to state that let p be an arbitrary prime number. Okay. Then we're going to assume P is not odd. So we're negating, there's two S's in assume, sorry. Assume P is not odd. So we're negating what we're saying here, that P is odd. Okay, so we're saying assuming it is not odd. Now our first statement, what does this mean now? So P is divisible by 2. Or another way to say this is that P is a multiple of 2. Okay? So, or we can say P is a multiple of the number 2. Same thing. Okay. So P is prime. Since P is prime, it must have exactly 2 divisors. It has 2 as a divisor and obviously 1. So since it's prime, we're now zooming into the fact that it's a prime number. Since it is prime, it has exactly 2 divisors. And what are those divisors? Well, it has 2 as a divisor, so P must be divisible by 1, only 1 and 2. Okay? So it has exactly 2 divisors. Remember, it's an even number. So we said it's divisible by 2. So P has divisors 2 and 1. Those are the 2 divisors that P has, because it's a multiple of 2. So 2 and the other thing has to be a 1. Now remember, there's a problem here. This means that P is therefore equal to 2. Okay, now did that prove what we set out to prove? Let's see. For every prime number P, if P is not 2, then P is odd. So we're saying, let it be an arbitrary prime number. Assume it's not odd. Okay, so we're negating that. We're proving the contrapositive. So P is divisible by 2 then, because it's not odd. And since P is prime, it has exactly 2 divisors, which means that P has divisor 2 and 1, which means the number that I'm working with here is indeed equal to 2, which negates that. Therefore, what did we just prove? We proved that for every prime number P, if P is not 2, then P has to be odd. So this here is a proof by proving the contrapositive. Okay, folks, you can see it's a little bit tricky to think about what it is, how you're going to change the statement, and what you do with what's given. You turn it, I just rephrase it here, and for the purposes of formulating a contrapositive proof. So we were assuming that there's a prime number P, we're assuming that it's even, and then showed that if it's even, it can only be 2, which is what we did here. So we proved that statement by proving its contrapositive is true. Now remember, if P, not P, then not Q, shows you that is the contrapositive of the statement. If Q rather, then P. So that's what we proved. We wanted to prove that, and instead of proving this, we proved its contrapositive. Why does it work? Because these are logically equivalent statements.